Hello, thanks for clicking and welcome back. Today we're going to continue our discussion of limits. We're going to pick up where we left off yesterday when we talked about how to calculate a limit graphically and add a few more things to that. And then we're going to go on and discuss what we call the limit laws, all right, which really dictate the operations that you can do with limits. So first, yesterday we talked about how to calculate a limit graphically, and we also saw that some limits do not exist. Today, we're going to talk about all of the types of limits that do not exist. Okay? There's one set of limits that you already know. Limits whose behavior differs from both sides. Okay, now you've already seen that. You saw that yesterday when we did the graph. So for example, if I had, here was my graph, we'll make it something simple looking. Okay, and then here we go. All right, here's my graph called f of x. And if I were to ask you what is the limit as x approaches 1 of f of x, you would say, all right, well, they're not telling me which side I have to approach from, so I'm going to have to try to approach from both sides and make sure that it's the same. So if I calculate the limit as x goes to 1 from the left of f of x, right, the little negative sign meaning from the left. So from the left, I work my way across the graph, and the limiting value, I am approaching the y value of 1 from the left. If I ask you then to calculate the limit as x goes to 1 from the right, I'd come in this direction, so I'd start on this path, work my way down, and I'm approaching the y value of 2. These two limits are not the same from the left and from the right, so we would say that this limit as x goes to 1 of f of x simply does not exist. All right? That is the first type of limit that does not exist. The behavior differs from both sides, which is what we saw yesterday. All right? So there's the first one. Let's talk about the second one. Now, the second one, we really didn't talk about yesterday. I didn't even mention it, but there's a reason for that. The second type of limit that doesn't exist is a limit that has unbounded behavior. So what do I mean by that? Well, like I said, we actually saw this yesterday. Asymptotes and graphs at asymptotes. So let's say this was my graph. I'll call it f of x. And I were to ask you, what is the limit as x approaches 2 of f of x? Well, you would say, okay, well, from the left and from the right, it doesn't say, so I have to try from both sides. If I try the limit as x goes to 2 from the left of f of x, now from the left means follow this piece, work my way all the way up. This graph goes to positive infinity. Okay, the limit as x goes to 2 from the right of f, from the right, work my way up, and the graph goes up. This graph goes to positive infinity as well. Now the limits go to the same place from the left and from the right. They both go to positive infinity. So we would say that limit approaches positive infinity. Now, mathematically, technically, these are all types of unbounded behavior. This limit does not approach a finite value, right? It approaches what we call positive infinity, or it could approach negative infinity as well, just that this graph happened to approach positive infinity for both sides. Okay? Technically, these limits all do not exist. None of these limits actually exist. However, the rule of thumb is if you can describe the direction of the graph based upon the limit that's been asked, then you're told to do so. So I was asking you for the limit as x goes to 2 from the left of f of x. You were able to say, yeah, as x goes to 2 from the left, this graph goes to positive infinity. So you told me so. Okay? Again, technically the limiting value it doesn't exist because there is no value that it approaches, right? It approaches positive infinity. That's not an actual numeric value. However, since we can describe where it goes, we describe it, okay? Now, let's say, for example, that my graph looked like this instead. Let's just change it up a little bit. Well, let's go back here again and talk about some of these. The limit as x goes to 2 from the left would still be positive infinity. The limit as x goes to 2 from the right now, well, this graph goes to negative infinity. Again, technically, this limit does not exist, okay? But we can describe the direction of the limit. So we describe the direction of the limit to negative infinity. This limit as x goes to 2 from the left and from the right. I don't go to the same place. So this limit does not exist, right? Because the first type of limit said the behavior was different from both sides. So you would only write DNE for this answer, okay? Because from both sides, it doesn't go to the same place, so the limit does not exist. I can't describe one direction or one place that this limit is headed to, or this graph is headed toward. All right? So it's a little bit subtle there. Okay? Technically, all these limits don't exist, even though they say positive or negative infinity, but we can describe the direction it goes to, so we're asked to describe it. Okay? That's your second type of limit that doesn't exist. And then there's one more type of limit that doesn't exist. It's a limit that has oscillating behavior. All right? So what I encourage you to do is I encourage you to graph. If you have a graphing calculator, put it in radian mode. Calculus is only done in radians. All right? Calculus is done in radians only, no degrees. Put it in radian mode and graph sine of 1 over x. If you don't have a graphing calculator, you could, of course, go to the online calculator, right, which is desmos.com. You go to Desmos, and you can type in sine of 1 over x. All right? I want to calculate the limit as x goes to 0 of sine of 1 over x. Okay? So I've actually graphed this in my graphing calculator. I'm going to show you what I see. All right? So I have it graphed already. Let me show you what I see. And if you take a look, this graph has been zoomed in twice already. Okay, it's already been zoomed in twice. Oh, sorry, it's hard to see. All right. It's been zoomed in twice, but hopefully you have a better picture for you. But if you look at x equals 0, here's x equals 0 over here. That graph does not approach anything. Okay, it just looks like a bunch of lines that just keep back and forth, back and forth, back and forth, back and forth. It does not look like this graph approaches anything at all as x goes to 0 from the left or from the right. So we would say that the limit as x goes to 0 of sine of 1 over x simply does not exist. This does not approach a value. This function does not approach a value as x goes to 0. Okay? So that limit does not exist. That is the third type of limit that does not exist. Okay? Those are your three types that you're looking for. All right, if you want to write DNE. Those are really the only times you should write DNE. Okay? That's it. No other time should you write DNE. All right, now, let's move on a little bit and let's start talking about what we call the limit laws. The limit laws allow you to do operations on limits, okay? They allow you to do operations on limits, all right? So you actually have a handout that has all the limit laws on there. I'm gonna write a couple of them out just for the sake of writing them out. To do this, the first thing you have to do is you have to assume the limit as x approaches. In the handout, it says a, so that's fine, of f of x, and the limit as x approaches a of g of x both exist. Okay, so they have to give me some kind of finite value. They have to give me an answer. All right? Now, again, take a look. Look at your notation. Your notation is important in this class. The limit as x goes to a of f of x. This means that as x approaches a from both sides, right? I have to go to the same place on the graph of f of x. Same thing with g of x. On g of x, from both sides as I get closer to a, have to go to the same y value. They have to approach the same y value, right? Okay, because it's not saying from one side or the other. So I have to distinguish. All right, so let's talk about a limit law. Here's a good example, a simple example of a limit law. A limit as x goes to a of f of x plus g of x. So if I want to find the limit as x approaches a of the sum of two functions, I can do that by finding the sum of the limits. You could take the limit as x goes to a of f of x plus the limit as x goes to a of g of x. Okay? That's an example of a limit law. All right? They all pretty much work the same way. You can look on your handout that I gave you. Okay? They are important. You will use them. All right? We'll be using them today, and we'll be using them throughout the year. Okay? But they are pretty simple to understand where they're getting them from. All right. The one that's the most popular that we tend to use the most, because of another rule that we're going to talk about later on this year, is the quotient. The limit as x goes to a of f of x over g of x is the limit as x goes to a of f of x divided by the limit as x goes to a of g of x. Okay. The limit of a quotient is the quotient of the limits. All right, so this one we tend to use a lot. All right, but all of them we will use at some point or another. All right, so let's see how that plays into what we know. Okay, let's see how that plays into what we know about finding limits graphically. Okay, all right, so here I have a graph. All right, this graph, okay, has two functions on it. F of x is in black, and g of x is here in blue. Okay, so now I got two functions I'm working with, f and g. Let's first simply calculate the limit as, let's say, x goes to -2 of f of x plus g of x. So I want you to calculate for me the limit as x goes to -2 of f of x plus g of x. Well, then that would equal to, by the limit laws, the limit as x goes to -2 of f of x plus the limit as x approaches -2 of g of x. Now, the first thing you need to be careful of is you need to make sure that both of these limits actually exist, right? Because if these limits don't exist on their own, the limit law that you just wrote here doesn't work. Okay, what you've just written is false. So the limit as x goes to -2 of f of x means from both sides, I have to be going to the same place on f. So as I approach -2 from the left, I go to 1. As I approach -2 from the right on f, I go to 1. So the limit as x goes to -2 of f is 1. Plus, the limit as x goes to -2 of g. Well, from the left, I'm going to -1. From the right, I'm also going to -1. So that limit is -1. -1 plus 1 is 0. So the limit as x goes to -2 of f of x plus g of x must be 0. There's my answer. That seems pretty silly and pretty simple, right? I hope so. Okay. But let's try another one. And before we do, or as we do, as we're erasing here and getting ready to write again, okay, one of the most popular questions I get is, of course, well, do I have to write everything out? Do I have to write the limit law? Yes, that's what it's there for. Okay, you can't do this unless the limit law is actually there. So let's try the limit as x goes to 1 of f of x. Let's do f of x times g of x this time. All right, we haven't talked about that one yet, the product. So the limit as x goes to 1 of f of x times g of x is the limit as x goes to 1 of f of x times the limit as x goes to 1 of g of x. All right, so now let's go over here and make sure both these limits exist. The limit as x goes to 1 of f of x from the left is 2. From the right is also 2. This limit is 2. The limit as x goes to 1 of g of x. From the left is -2. From the right is 1. This limit does not exist. So we cannot continue in this fashion the way we are working. Okay? We cannot calculate the limit as x goes to 1 of g of x. So we cannot continue. However, what we could do is we could try and figure out. So let's get rid of this. We can't do this anymore. It's not going to work. But if I want the limit as x goes to 1 of f of x times g of x, well, to figure out what that limit is, I could do this. The question is, could I find the limit as x goes to 1 from the left of f of x and multiply by the limit as x goes to 1 from the left of g of x? Well, I guess I could, but for the limit as x goes to 1 of f of x times g of x to exist, then that would also mean that I'd have to calculate the limit as x goes to 1 from the right of f of x times the limit as x goes to 1 from the right of g of x. These two would have to be equal to one another, right? Because for this limit to exist, from the left and from the right, I have to go to the same place, okay? So is it possible that the product of these two go to the same place? Perhaps, but we'd have to see. So let's try the limit as x goes to 1 from the left of f. As x goes to 1 from the left of f, you get 2. The limit as x goes to 1 from the left of g. Comes down here, you have -2. 2 times -2 is -4. So this limit is -4. The limit as x goes to 1 from the right of f is 2. The limit as x goes to 1 from the right of g is -1. That's -2. So I have two limits. From the left, I get -4. From the right, I get -2. These two are not the same, which means the limit as x goes to 1 of f times g does not exist. Because from the left and from the right, I go to two different places. So that will not work. Okay? All right. That takes care of how to use the limit laws graphically. Okay? You can do that. You can practice it. All right. Now, final thing today is we are going to talk about how to find a limit by table. So we're going to actually start talking about how to calculate a limit algebraically, numerically, as opposed to using the graph each time. All right? So let's say I asked you to calculate for me the limit as x goes to 2 of x squared. Now, you're saying, it probably should be pretty easy, right? If you had a guess, you'd probably take a guess it would be 4. But remember, we're just starting out, and limits mean what value, y value, do you approach as you approach the x value of 2, in this case, from both sides, right? From both the left and from the right. So let's actually do that. We're actually going to go and we're going to take the function f of x equals x squared, and we're going to make a little table, all right? We're not going to do this often, but we're going to do it for the first time here. So we're going to make a table with some x values and what we get for f of x. We're going to use 1.9, we're going to use 1.99, and 1.999. So these are all values from the left. We agree? Okay? These are from the left. All right. And again, from the left algebraically, I mean, here's 2, right? Here's 2 on your number line. So from the left means getting closer to 2, smaller than 2, and getting closer to it. So from the right, so this is the value we don't know. All right, we know what f of x is, but we don't know what the limit is. So we'll just put a question mark there. From the right, we'll use numbers like 2.001, 2.01, and 2.1. Okay, this is from the right. So this direction is from the right. Okay, just bigger than 2, working your way back toward 2. All right, so let's just plug these numbers in. You can plug them in. I already did, just for the sake of time. All right, let me put down what answers we got. This one we don't know. Who knows what it is? That one's that. And then we have 4.0401. And then we have 4.41. Okay. So now, what does it mean to calculate the limit as x goes to 2 of x squared? It means that from the left and from the right, I have to go to the same place, right? Same old definition we've been talking about. So what is the limit as x goes to 2 from the left of x squared? Well, from the left, as I approach, here's the y values, 3.61, 3.9601, 3.9960001. It looks like I am getting closer to 4. From the right of x squared, I'm at 4.41, 4.0401, 4.004001. I'm sure the suspense is killing you. It looks like I'm getting closer to 4. So it looks to me like the limit as x goes to 2 of x squared should be 4. And in fact, it is. This is the correct answer. Okay? This would be your correct answer using a table. And then from here, what we're looking to do is the following. We're looking to something called direct substitution. This is one of our best friends to algebraically calculate a limit. Direct substitution. Because direct substitution is exactly what it sounds like. It says that the limit as x goes to 2 of x squared can be calculated by taking 2 and squaring it, which is 4. Okay? That would be what we call direct substitution. All right? That's it for now. We're going to pick up with direct substitution and how that works and what pitfalls we run into with that next time. As always, thanks for clicking.